I'm Trevor Evans, a PhD student from the University of Toronto, and this is a short presentation on discretely relaxing continuous variables for tractable Variational Inference, a new paper appearing at NeurIPS 2018. This is joint work with Prasanth and Nair. The ability to perform energy and resource-efficient inference is extremely important. For example, machine learning applications on mobile devices often require robust inference in real time. However, these devices have strict limitations on computational resources. We introduced a fast and efficient technique with discrete variables that can substantially improve resource efficiency. Continuous priors are typically used for approximate Bayesian methods because of the availability of computationally tractable training strategies, such as the reparameterization trick. Conversely, models with discrete priors are challenging to train. However, they offer resource-efficient inference since posterior samples will also be discrete, allowing representation as quantized integers that are often sparse. The strategy we introduce allows these discrete models to be trained extremely efficiently, allowing us to discretely relax continuous priors to perform tractable variational inference. The reason that training is typically challenging is because of the sheer size of the hypothesis space. That is, the total number of values the model variables can take, which increases exponentially with the number of variables in the model. This is problematic because of variational inference optimization objective. The evidence lower bound, or ELBO, requires evaluating the model's log likelihood at every single one of these points in the hypothesis space. Of course, this quickly becomes intractable, and so historically the ELBO is approximated by a stochastic estimator, and available estimators for discrete models often leave the optimization process swamped in extremely high variance gradient estimates. On the other hand, we demonstrate how the ELBO can be computed efficiently and exactly. To do this, we first view the log prior, log likelihood, and variational distributions at each point in the hypothesis space as an entry in a b-dimensional tensor, where b is the number of variables in the model. We then identify and exploit low-rank structures of these tensors to rewrite the ELBO in a compact form. Conveniently, when we rewrite the ELBO in this compact form, we eliminate all dependence on the number of training points, so we can train on an arbitrarily large dataset without affecting training time. We call this the direct approach, and while it is not practical for all likelihoods, we identify a couple of models that are practical, for example, the popular class of generalized linear models with a Gaussian likelihood. In summary, the proposed direct approach enables exact computation of ELBO gradients, eliminating variance and allowing the use of quasi-Newton optimization methods. Its training complexity is independent of the number of training points, permitting inference on large datasets, and its posterior samples consist of sparse and low-precision quantized integers, which permit inference on hardware-limited devices. Our studies demonstrate accurate inference using variables discretized as extremely low-precision 4-bit quantized integers, and we train on datasets with over 2 million points in just seconds, even though the ELBO computations require a number of log likelihood evaluations equal to the number of atoms in the universe raised to the power of 30. We demonstrate the direct approach both for mean field variational inference as well as for unfactorized variational distributions. Code is available, and I look forward to seeing you at NeurIPS.